4x, multiples of 4, modulo 10. Now, 10 is not prime. But now, 4 and 10 also have common factors. So 4 and 10 are not relatively prime either. I want to draw the picture of what happens if I take residue classes mod 10 and multiply by 4. So here are my residue classes mod 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. My arrow now is a times 4 arrow. I want to look at this picture and see what's happening. If I take 0 times 0, that's 0. 1 times 4 is 4. 2 times 4 is 8. 3 times 4 is 12, which when I then divide by 10, the last digit is 2. Okay? 4 times 4 is 16, so that ends with a 6. Ends with a 6 because I'm doing mod 10, so it's easy. 5 times 4 is 20, so it ends with a 0. 6 times 4 is 24. 7 times 4 is 28. 8 times 4 is 32. And 9 times 4 is 36. Oh, if we look at this picture, again, I want to repeat some of the nice observations from before. What is still here and what is no longer here? It's still symmetric. Actually, here you can really see how symmetric it is when I go around this line. Of course, it's still symmetric, because why was it symmetric? 9 was minus 1 mod 10, and 6 is minus 4 mod 10. So of course it will be symmetric. But my loops are all gone. I cannot take loops anymore, because if I see what's happening, the 1 goes into this 4, 6 loop, but nobody goes into 1. What a shame. What this means is that all of what we have done before with loops requires that these two are relatively prime. It also means something else. It means that if I write down an equation, suppose I want to solve for x, find x, where I take 4 times x is congruent to 7 mod 10. This has no solution. It has no solution because if it had a solution, that would need an arrow going into 7. Would need that there was some arrow going into 7 in order for that to have a solution. And you see this 7 has no arrow going in. What does that mean? This means that it's not possible to divide both sides of this equation by 4. You see, before I said with these 3 equals, with the 3 equals, it looked like equations that you can add and subtract. You can. With equations like this, you can always add and subtract. Okay, let me remind on that. If I write for you things like 26 congruent to 46 mod 10, and I tell you another one, which is something like 12 congruent to minus 8 mod 10, I can add these, no problem. The reason I can add these is because the gap, each of these notations means that the gaps are all multiples of 10. And so if I add them together, the gap will still be a multiple of 10. And we even see 38 congruent to 38. Oh, really? I didn't do that on purpose. But both, this is definitely true. They're both 38. Okay. But you can also take 2 of these and you can subtract them as well. So I won't do that here, but I'll say minus is also okay. if I have two of these, I can also multiply them. Okay, multiply is okay. Maybe instead of actually multiplying these two numbers, let me explain why multiplying is okay. So if I have these two numbers, okay, the fact that these two are the same, why multiplying is okay, is because the fact that these are the same means that 46 equals 26 plus some multiple of 10. I'll call that a. Okay, that's what this first equation means, with a is an integer. I also know that minus 8 is equal to 12 plus 10 times b, which is some other integer. Well, what that means is that if I wanted to multiply 46 times minus 8, well, that would be multiplying these two things. So I will get 26 times 12 plus all the other things have 10s in them. So I have 26 times 10b, that's not a 6, plus 12 times 10a plus the 10a, 10b. 10a times 10b. But all of these things on the right-hand side, all of these have 10. This is a multiple of 10. And that's why 46 times minus 8 is the same as 26 times 12 mod 10. So if I have these modular congruences as equations, plus, minus, times are all okay. Divide becomes a problem. And the reason you can't divide is because back here, I can't divide this by 4, mod 10. There will be cases when I can divide. But I want to show first, be very careful when you divide if the 4 and 10 are not relatively prime, like in this picture. And so, because of the fact that right here in this picture, this has no solution, what this means is I can't divide by 4. Okay? So that does not exist here. There's no way to divide by 4 in this picture, in this mod 10, modulo 10. Okay? Again, all I can do is plus, minus, and times. So the punchline here is that you need to be very careful when you have 4 and 10, which are not relatively prime, because some of these have no solution. Well, what if you have a solution, though? What if what happens is you don't have 4x equals 7, mod 10, but what if we had a different problem, which was the 3x equals 7, mod 10? That equation we can solve. Let's go forward, and let's say, suppose I'm trying to find out what is 3x, solving 3x equals 7, mod 10. For this, let's remember the picture we had, which would tell us what I could multiply. Well, no. To do this, let's actually try to draw a picture very quickly of what happens when I multiply by 3. So here I'm drawing my residues, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to very quickly draw the multiples of 3 here. So I take 1 goes to 1, 1 goes to 3, 2 goes to 6, 3 times 3 is 9, so I go over here. 4 times 3 is 12, so it goes back here. 5 times 3 is 15, back to itself. 6 times 3 is 18. 7 times 3 is 21. 8 times 3 is 24. And finally, 9 times 3 is 27. I guess it took the longest to get there. But this is interesting. Over here, remember the picture here was that everyone has exactly 1 in and exactly 1 out. What that means is that over here, there is a way to multiply 3 times something to get 7. You can solve this. And not only can you solve this, this has a unique solution. 9 is the only solution. So this thing here has a solution, and I will write that it is unique. Unique residue. Okay? There's exactly one going in. This is where I'm using the fact that here, since 3 and 10 were relatively prime, I used that every residue class has exactly one in and one out. That's how I know there's exactly one way to do this. There's a unique solution. Okay? If I go to the other one, if I go back to the other problem, when I go modulo 10 with 4 times something, sometimes there's no solution, but worse, sometimes there is a solution and it's not unique. For example, if I look at this question over here, and I say I want 4 times x is congruent to, let's say, 4, again, these are all mod 11, you can see that this has 2 solutions. Both 1 and 6 go inside here. So this has non-unique solution. It has multiple solutions. So not only can you sometimes not find solution, sometimes you have many. And this is what happens when you have the not relatively prime. I want to emphasize what's going on here is I cannot divide by 4. If you could divide by 4, division means I take something, divide something, and I get an answer, always the same answer. But let me go back to the 3. I can divide by 3. Even though it's mod 10, I can divide by 3. But I need to define for you, what does it mean, divide by 3? On this, we have to remember what division means, even with normal numbers. With normal numbers, division means multiply by the inverse. What I mean here, divide by 3 is the same thing, if it's well defined, divide by 3 is the same thing as multiply by 3 inverse. Sometimes we write like this, 3 inverse, 3 to the minus 1. In this picture, I'll tell you what is 3 inverse. 3 inverse is 7. Why is 3 inverse 7? Because these arrows are the times 3 arrows. And one of these times 3 arrows ends up at 1. Think about what 3 inverse means with normal numbers. With normal numbers, 3 inverse is take that number times 3, get 1. This has that. 7 times 3 gets 1. Then I can use this to solve this equation. You see, I have this equation, and I now know an extra piece. I have learned from this picture that 7 times 3 is 1 mod 10. Okay? That was the very important conclusion from this picture. 7 times 3 is 1 mod 10. Well, I'm trying to solve an equation, 3x equals 7 mod 10. I know this. I also need to solve this equation, 3x equals 7 mod 10. Well, I told you already that you can take these modular equations and multiply both sides by anything you want. So let's take this and multiply both sides by 7. It's okay. Multiply is okay. Divide, you have to be careful. But you can always add, subtract, multiply. So I choose to multiply by 7. I choose that because I already know 7, 3 will give me 1. This is the power of the multiplicative inverse. That's what this is called. Multiplicative inverse, which I wrote as 3 inverse, which was 7 mod 10. Okay, so when I have this multiplicative inverse, I can multiply. 7, 3 already gives me 21, which is 1. I already knew that. I knew that would be 1. 1x is 7, 7, 49. Mod 10. Well, that's 9, which agrees with what we had found before. Before, we found that it was 9. That one we found by looking at the picture. This one, if you know the inverse of 3, any such equation you can solve. Because if I want to solve another equation, I'm making another one up right now, 3x congruent to 5 mod 10. Well, I already know the multiplicative inverse of 3 is 7 times 7 on both sides. 7, 3 cancels, and you just have the x. 7, 5 is 35. So mod 10. Let's check, is that true? If I go back, yes, 5 times 3 comes back. So this is the power of what happens when you can divide by 3. To finish this and bring everything in this lesson together, what happened with 4? You see, with 4, 1, nothing is going into 1. So with 4, 4 has no multiplicative inverse. There is no way to take 4 times something and get to 1. There is no 4x congruent to 1 mod 10. That's why I couldn't solve these equations. 4x equals 7. I couldn't multiply 4 inverse. There is no 4 inverse. That's why here there are multiple solutions, because there's not a 4 inverse I can multiply. So in all of these pictures, 1, that is the one that controls everything. No arrow into 1, then I cannot always solve such equation. And this is the story, the complete story of what modular arithmetic looks like when you go modulo primes, modulo not primes, when the thing you're multiplying by is relatively prime or not. I encourage you, we have talked through all of this. The best way to really understand is also to try it yourself. These are very easy to draw. Actually, I just drew these right before the class I gave you. And when you draw these pictures and try the multiplications, you can even find for yourself why all of these things work.